In large and complex communication networks, a fault in one part can negatively impact the entire network. However, in such cases, it's not easy to predict how the network will behave in advance. There is in fact a method that solves such a problem. It's called chaos engineering. Chaos engineering does not predict. Instead, it intentionally injects pseudo-faults into the network and observes its behavior. It analyzes these observations and develops countermeasures to build a network that can withstand faults. Chaos engineering involves 4 steps: hypothesis, experiment, analysis, and improvement. In the hypothesis step, you define the steady state of the network and the faults you inject. You hypothesize that even if the assumed faults occur, the steady state can be maintained. In the experiment step, you actually inject the defined faults into the network. In the analysis step, you check the state of the network after the experiment and analyze whether the steady state has been maintained. If the steady state has not been maintained, you reconfigure the network in the improvement step in such a way that the steady state can be maintained. Currently, both the experiment and analysis steps are automated. On the other hand, the hypothesis and improvement steps are not automated because they require extensive knowledge and a high level of skill. To solve this problem, NTT Network Services Systems Laboratories is focusing on LLMs' ability in reading, code generation, modification, and planning, and is developing a system that uses LLMs to fully automate chaos engineering. This is a schematic diagram of the system. The flow of each of the 4 steps is predefined, so the user only needs to enter the Kubernetes manifest, which describes the network structure, and inform the system of their intentions, written in natural language. After that, the LLM autonomously performs the task, outputting a Kubernetes manifest that satisfies the hypothesis and a summary of the process of the experiment and modification. Let's look at each step in more detail. In the first step, hypothesis, the LLM defines hypotheses appropriate for the input Kubernetes manifest. The LLM defines 2 hypotheses, the steady state of the network and the assumed faults. It also produces unit tests that will be used when verifying the steady state in step 3, the analysis step. Next, the LLM creates an experiment plan. The plan outlines when and how long to run unit tests to verify the steady state, as well as when and for how long to inject faults. In the second step, experiment, the LLM converts the experiment plan into a workflow file for Chaos Mesh, a tool for setting up the faults, as you can see here. After the conversion, the experiment is carried out. In the third step, analysis, the LLM analyzes the experimental results and verifies whether the unit tests have been passed as required. If they have been passed, the input network structure has no problem. So, the Kubernetes manifest and a description of the analysis results are output. If there is a problem, the LLM analyzes the cause and proceeds to the 4th step, improvement. In the improvement step, the LLM rewrites the Kubernetes manifest based on the analysis results so that the network structure will satisfy the hypotheses. After that, it goes back and repeats the experiment, analysis, and improvement cycle until the hypotheses are satisfied. Finally, it completes rewriting the Kubernetes manifest into one that satisfies the hypotheses and outputs it along with a description. Going forward, we will apply the system to more complex networks and advance each step of the chaos engineering process.